And that's it for the housekeeping. And with that, what I'm going to do is I'm going to go ahead and pass it over to Team Qosmo, and they're going to show you how to build a audio plugin, a neural audio plugin using Neutone. Over to you, Team Qosmo.
Yeah, thanks very much, Josh, for that introduction and for going over the NAP competition as well. Hopefully, a lot of people will find that information useful and will get excited about contributing to the NAP competition. And hopefully, through these workshops as well, like we can really educate people and give them the tools and the know-how to build some really sick models during this competition and for them to submit to the competition. So anyway, let's get started with the workshop for today. So I'm just going to share my screen. So yeah, welcome everyone to the second live stream. And this week we're doing the workshop. So yeah, ourselves from Qosmo giving this workshop on Newton, and then we've got Gabrielle giving the workshop on the MATLAB toolkit stuff as well. So very exciting week and a lot to share with you today. So this workshop on Newton, which is a real-time AI audio plugin and SDK. If you don't know who we are, this is the lineup of our speakers for the Neutone workshop today. So there's myself, Andrew Fife, who's an AI application engineer at Qosmo, and I'm also a PhD researcher at the University of Glasgow. We've got Chris Mitchell-Tree, who's also AI research engineer at Qosmo and PhD researcher at Queen Mary University of London, and Naotake Masuda, who's a AI research engineer at Qosmo and PhD researcher at the University of Tokyo. So yeah, you can obviously feel free to ask us more about our PhD research, but it's all in the realm of sort of AI audio and neuro audio. So yeah, we're all equally as passionate about these sort of technologies. So today's agenda, we've got quite a lot in store for you. It will initially be with myself, giving you an overview of the Newton platform, the different components that make up Newton. I'll then dive into the plugin, give you an overview of the Newton plugin, what models are available currently, the features that are available through the plugin, and then I will give you a live demonstration, and hopefully it goes well. You know how live demos go, but looking forward to having a play and you know show you guys all the crazy and creative stuff you can get up to using the Newton plugin. And then I'll hand it over to Chris, who's going to talk to you about the Newton SDK, walk you through the workflow for building a model and all the features and information that is there to do with the SDK. And so you're well equipped to navigating the SDK and building models for Newton. Then I'll pass it over to Naotake, who's going to give you a proper in-depth sort of overview of the different neuro audio models that we currently support, and also a sort of end-to-end model wrapping process, so you can see with a simple example how you can build a model, wrap it for Newton, and import it and use it as part of the plugin. And then we'll wrap up with some community contributions so far, like what you guys have done so far with Newton, and discuss some of the things we'd like to see going forward, and you know the features we'd like to bring to Newton, the kinds of models we'd love to see you guys submit, and yeah, we'll be open for questions at that point. So let's get started. So what is Newton? For those that don't know, Newton is a platform that's really aiming to bridge the gap between the AI audio research community and artists and musicians and producers, like the creatives that want to actually harness and use these technologies as part of their creative workflows. So this is it here. We've got the audio creators, the musicians who are jamming out like with the tech, and then we have the AI researchers who are innovating in this space, and a lot of the time these are quite disconnected. areas, and a lot of the creators who are wanting to use the latest technologies to explore and express themselves in new ways can't access them, or they're not available. And same for researchers. Researchers may want to actually try and get their technologies into the hands of creatives quicker, and also to iterate on their model building process. They may want to use a tool that can really streamline the workflow for iterating and improving their models. So this platform addresses those sort of key areas. We also have a community which brings together these, the artists and the musicians with the researchers and devs into the one space, so that we can communicate and, strive to build better and better models and more useful and impactful tools for creatives. So yeah, make sure to check out the Neutone.space website, where we have all the resources, the download links for the plugin. We have some blogs there, and just all the information regarding Neutone is on that website. There's also the link to join our Discord as well, where all the conversation's happening. So be sure to check that out as well. And the main reason we decided to build a platform like Neutone is because in the past couple of years, this space has been so fast evolving. Like, we've seen really heavy neural audio models that had been innovated initially, that were running that weren't fast enough to run in real time, so, or maybe less appealing to some creatives to use. But we're into this territory now where we've got algorithms and neural network algorithms that are coming out that are running in real time, and that opens up a whole new dimension of expressiveness for musicians, and being able to perform these models in a live context as well. So these are just two examples of some of the innovations that have came out in the last couple of years. We've got DDSP, which is both these models, are this a timbre transfer kind of model. So this is the concept, or this idea of translating an input sound to some sort of output sound. So you can imagine maybe like a drum sound being translated to speech, or like piano to violin. It kind of works in that sort of way. So we've got DDSP, which works on monophonic signals. And we have Rave as well, which is also another timbre transfer effect, which can work on a multitude of different kinds of signals as well, and runs at 48 kilohertz sample rate. And it's just a really fast evolving field of research. So there's more and more algorithms coming out all the time. To give you an example, this timbre transfer effect that I was mentioning earlier, this is I guess an example for you to listen to. Hopefully you can hear this. So this is using DDSP. We've got a violin here and coming in at the input, and it's been translated to like a shakuhachi flute sound. So this sounds like this. And that's been translated to this sound. And then the same for Rave. We've got, in this example, violin being translated to speech, so the violin. And then translated to speech. So yeah, a lot of fun there. You can kind of get an idea or intuition on how these timbre transfer effects work. So currently, one of the main reasons we decided to build something like Neutone is because for those who were interested in applying neural audio effects to their creative workflow, or for even wanted to get these neural audio effects to run as part of the DAW, it was a really cumbersome and time-consuming process. Usually, it initially start with building a model in, say, a framework like a deep learning framework like PyTorch. You need to train that model, which again is potentially a costly procedure. take a long time to train a model to a level of fidelity that might be useful. It requires some GPU acceleration, and yeah, sometimes it's costs and time that you don't have. Again, like we haven't like catered for a solution that like handles this exactly, but like it is part of the process which you need to be involved in normally. And then once you've trained a model, you would typically run inference on that model to get a result. So say you've got some input audio and you want to like run it through your neural network and get some output, you would need to run that through the command line using some, an inference script that would run inference on your model. And then by that point, if you survive, you can actually, use that WAV file and drop it into your DAW and actually start being creative with it. But as you can see, it's quite a cumbersome process, not very streamlined. There's lots of obstacles and friction. And yeah, we tried to address a lot of this with Neutone, tried to streamline this whole process for researchers and those interested in deploying neural audio models in the DAW environment. So, and I should say on top of that, developing audio plugins requires that expertise and knowledge as well, on top of all the ML stuff. So again, it's like quite a lot of different skills that are required to build a plugin that would use neural audio technologies. So again, Neutone is a solution to those that maybe have great ideas and skills in the ML world and want to just build a model and get it in the DAW as quick as possible. So here is our release video for Neutone. And I always love showing this off, at, these sort of workshops and presentations, because it really showcases how musicians and artists can find value using Neutone in their creative process. So this is Big Yuki, who we partnered with, as part of his creative process, using Neutone to compose new music and also for live performance. So I'll play this first, and you'll get a better idea, understanding on how Neutone can be integrated into the creative workflow of musicians.
この本には2小節の音楽の断片が多数収録されています。サイコロを2個振って出た値によってこれらの断片を並べていき、一つのまとまったが
What's up? Big Yuki here. And man, Neutone is the happy accident. It gives me all kind of new ideas. I can't wait to write some crazy using it. Stay tuned.
Oh shit!
Yeah, so as you can see, Big Yuki there having a lot of fun. I always love how, that sort of surprise he gets from like working with the models as part of his creative processes. Because this is such a new space, new territory, there's so much kind of exploration that goes on with working with these technologies, which is always great to see. So moving on to the plugin, I'll give you an overview of this, all the key components of the Neutone plugin, and then we'll dive deeper with a demonstration. So I should start off saying like the Neutone plugin is available as a VST3 audio unit and standalone app. It's available for macOS, Intel, and ARM native, as well as now Windows 10 and 11, which we released quite recently. This is what you'll be greeted with when you open the Neutone plugin or app. You'll see here there's the model browser, where we list our catalog of available pre-trained models that you can just equip and use. And then to actually control and interact with the models, we have the control panel, which it swaps to the control panel once you have loaded a model. We have a number of different architectures and models in our catalog so far. So like mentioned earlier, we have DDSP models, rave models. We even have temporal convolutional network models as well, and plus a couple others. And these are all available and ready to use straight out the box. If you're a musician, producer, artist that just wants to start getting creative, they're all there and you can download them from within the plugin and then equip them, start using them straight away. Now to give you more of a overview of the different menus and components of the Neutone plugin. Like I mentioned before, we have the model browser where you have all the catalog of models, as well as you can filter and search for the models that you're particularly looking for. There's the ability to load your own model that you've trained locally. And also there's the About menu, which gives you more information, plus links to our resources as well. The filter option has, as well as searching, you can also, there's more advanced features that allows you to filter for certain tags, the author, the date published, and it sorts alphabetically as well. So you can use this feature to kind of explore what models are available. There's the About menu, like I mentioned as well, which shows the version ID, as well as gives links to our documentation, a link to our Discord community and social medias. And then once you equip a model, you've downloaded your first model, you've equipped it, it will take you to the control panel page. And this shows an interface, which is a range of custom parameters, global parameters, and presets as well. So just to give you more insight into what these are, we've got the global parameters, which are the larger rotary knobs there. They are controlling the audio inputs and outputs, certain parameters like the mix, so the wet and dry mix, the level of your input and output audio, and input gain and output gain, so the volume of your input and output audio as well. The custom parameters A, B, C, and D are sort of generalized with those names because those parameters actually hook into the specific model that you're using. So for each model that you equip, they all have different parameters that are specific to that model. So when you build your own model as well, you can export and assign the parameters that you want, and these will automatically be hooked up to the custom parameters here. To allow you to control your model. So yeah, I think we're at the Neutone plugin demo now. So I will come out of this first of all and share my Ableton Live session. So in this example, we've got a range of different sounds here. I've been playing about with some different variations. We've got a sort of pad-like sound, which I'll show you here if I bring down the wet and increase the dry here. So this is like our raw input sound. And then we've got equipped in this particular example, we've got this rave choir model. So just to kind of show you how I got there. When I launch the plugin, this menu comes up, and I've got a large selection of models that I've already downloaded. But yeah, essentially you just equip that model here. So you go like use. So this one is the rave choir model, takes you to this page, the control panel page, and then you can start interfacing with it. So that was the audio input that I just showed you. Let's see now what the affected sound sounds like when converted to the choir sound. So that's the sort of effect you get when running that pad-like sound through the choir model. Now, so we have a bunch of different parameters here that we've exported. They're quite technical, apart from maybe like chaos, which is quite an interesting choice for this parameter. I guess it's adding like random noise to the latent vectors. So let's play around with these parameters and see like what interesting textures and sounds we can get out of this. So yeah, endless fun there. And that was just like with a constant drone light pad, you know, and there's so much variation that you can get out of that. Let's move to another example, maybe something more percussive this time. So I'll mute that channel. Let's have a look at
As
this
you're
one.
doing that,
Yeah.
Andrew, we got a question in the chat
Oh yeah, go for it.
from Gary, who says, "What are the limitations and constraints on the input training signal? I.e., suppose I use my singing through a delay and a flanger as the input. Does that make any difference?"
Well, actually, that's I guess part of the exploration process of working with these sort of models. So, like, we've actually found that doing some processing of your audio in different ways. So, like doing a delay, maybe putting it through a chorus like effect, maybe adding compression. It all affects how that sound is translated in the output. So, you know, some models are actually trained on are trained on certain kinds of sounds that have particular qualities in like pitch and frequency information. So sometimes you actually get better results if you like do some pre-processing, like shifting the information into like a range that is more responsive with that particular model. Again, like if you want to play around with effects as well, you can, it all affects the generation of these neural audio models, like how they generate. So it's all part of that exploration creative process, working, you know, doing these pre-processing techniques to try and get more out of the models that you're using. So yeah, that's to give you an idea of like, we welcome that sort of thing. It's going to enhance the whole experience, I think, as a creative and artist working with this sort of tool.
Great.
Okay. So yeah, let's have a look at this example. I think I've got it equipped. Let's see. Yeah. So okay, so this one I have some kind of percussive sounds, I think. Oh, that's not what I want to do. There we go. So there's like grooving out on that. We have on the output a model which is trained on human voice, English sort of voice, I suppose, English speaking voice. So this percussive sound has been translated to sort of voice sound. So let's hear what that sounds like. So yeah, quite a strange kind of output, but let's play around with some of the parameters and see what other types of sounds that we can get out of this. So there was subtle variation there. Again, it depends on what model you're using, but like it's always interesting to hear like the slight changes in how the model is generating and responding to the input. Again, bringing down the input audio, you're getting like all these like whispers, and yeah, it's quite weird actually. Quite intense. Anyway, that was more percussive sounds. Let's move to another example quickly. This one was yeah, like a monophonic signal. I think it was let's hear what it was again. Oh, that's not the one. That is not the one we're looking for. We're looking for this one. Right, so it's like a bass lead. And on we've got the DDSP saxophone equipped for this example. So let's see how that sounds. So in this example, I can also remove the harmonics of this type of signal, and I only hear the sort of breathiness that's left, the sort of more, I guess it's also termed like stochastic sort of component of this sound. So let's hear what that sounds like. We can remove that. So yeah, that was a few examples of some, I guess, ways you could get creative with these sort of models. So we had 2 rave models there, different sort of use cases, percussive sounds, drone-like sounds, and we also had a monophonic sort of bass lead being converted to sort of a saxophone-like sound using DDSP. So I think that is the end of this particular demo. So I'll just show you actually quickly some of the options here. So like loading your own model. So Naotake is going to show you more about this later on when he takes you through building a model, but this is how you would import that into the plugin. We've got the filtering here. So we can actually just select tags for certain models. So there's also that, and then the about window where, like I said, mentioned earlier, you have links to our documentation, our Discord community, and social medias, as well as like the version number down there as well. And yeah, I think that is everything. So I'm going to come out of this demo now and get back to the slides. I'll probably be passing it over now to Chris, who's going to take you through the SDK and give you more insight into using the SDK and how to navigate the SDK and what features we have as part of the SDK. So I'll stop sharing now and pass it on to Chris.
Great. Thank you, Andrew. That was fantastic. All right, so I'm going to talk about the SDK a little bit. So the SDK is basically meant to make your life easy. Some of you may just be beginning to learn how to develop plugins, and some of you might be experts, but I'm sure this will be kind of a non-traditional approach to making a plugin, and I'm going to go over a little bit how Neutone does what it does. So as Andrew just pointed out, in the plugin you have at the top this load your own button, which is kind of where the SDK shines because it lets you write code in Python, not C++, to build a model. And this is because most neural networks and neural models are built using Python. The tools are very developed, and it's much easier to write your own neural network or audio processing system in Python than in C++. So the idea of Neutone is that it enables the user to easily write their model in the SDK with a bunch of help from SDK that takes care of a bunch of things that you might not want to deal with. And I'll go over some of those in a second. That you can focus purely on building something cool that sounds good. And then also very importantly is being able to test your model quickly and iterating, because that's a really big part of building a new audio effect is being able to hear what is going on. And that's currently another limitation with neural models is typically you have to be quite, literate with Python and how to run, scripts in the terminal to process some audio in a directory and then output the audio, save it somewhere, listen to what the output is, and then do that over and over again, which can be quite slow and probably is not the ideal way to prototype something quickly. But with Neutone, you can write a model, change a few things, export it in 10 to 20 seconds, load it into the plugin, and then hear immediately what's going on and change the parameters on the fly and get very real feedback. So I'm going to talk a little bit about the SDK and what it offers you. So the SDK is available on GitHub under Neutone _SDK. And it comes with a README that has documentation on, what it offers and some links on how to get started, which Naotake will go over a bit more. But basically, there's two things that you want to do. The first is you want to download the plugin from the Qosmo website and have that running in your favorite DAW or wherever you like to produce music, or just use your plugins. Then secondly, you want to download the SDK through pip is the easiest way. So if you're developing in Python, you can install the SDK with pip, or you can just download this Git file if you're more familiar with that. If you're not familiar with Python at all, then there's also Colab notebooks that we provide, which we'll also be going over in a second, so no worries there. And then here I'm going to go over the development workflow. So how does somebody who wants to build their own model, how would they do that using Neutone? So as I said, you go to the website, you find SDK, you might open one of the Colab notebooks that walks you through how to train a model, or you might load it up in your own local environment. Then you also go and download the plugin, which you can then load into your favorite DAW. For me, it's Ableton, so that's shown here. And then in the SDK, you would write your model in Python. It could be something very simple or something very complex. And then you would export the model using the SDK, which then will output a .nm file, so model.nm, which you can then load locally in the plugin. So you just on the load local model, and you can immediately start to use that model. And one thing that's nice is the model is automatically converted to C++, which then is compatible with the VST and the audio unit and whatnot. So this is kind of a loop, because you'll be spending time writing code in Python and only focusing on your on how you want your model to sound. So you don't have to worry about some of the other detail of building a plugin. And then you just load it into Neutone. It should work out of the box. You can try it out in different settings, different audio, different parameter settings. And then you can make changes and keep iterating until you're happy. And then once you're happy, you would submit it as a GitHub issue. We have a template. It's quite simple. You just go to the GitHub again and submit an issue, and you would upload the model that you trained, and then we would take a look at the code and just make sure it runs and works properly. And then we would upload it to Amazon 3, which hosts the models. And then from there, whenever anybody around the world loads up the plugin, it'll be available in the model browser. So you'll be able to use that model out of the box, and everybody else will be able to use it as well. So it's a really cool way to immediately share what you're using with all the other creative people that have the Neutone plugin. So that's kind of the workflow and life cycle of model development. So the thing that some of you might know is building a universal VST, or building a VST in general, is quite hard. I mean, that's why we have amazing communities like the Audio Programmer, because it's quite a steep learning curve. And as some of you might be familiar with, there's a lot of factors that need to be considered. So for one is that you have a DAW which has a bunch of settings that can change at any moment. And this includes the sampling rate of your DAW. So typical ones are like 44, 100, or 48 kilohertz. You have a buffer size of how many samples there are, and that also dictates delay. And you have to also, like your plugins have to communicate to the DAW how much delay they introduce, so that they can synchronize the tracks with all the other tracks. Otherwise, you get kind of a mess when you're playing back multiple tracks. And then on top of all of that, you need to be wary of your CPU usage, since you can't be, doing too many calculations that the audio doesn't come out in time. And taking care of all 4 of these things, also the parameters, for example, of a model need to be customizable. This is already hard enough for a single plugin, like a reverb, let's say, or a filter, right, which has a singular purpose. But with Neutone, we're trying to make any model possible. So we want to enable all models while still being able to handle these specific conditions. And this goes against kind of the paradigm of VSTs, which are typically very specific and have a very specific purpose that they were built for. And then finally, on top of all of this, we have neural networks, which can be flexible, but in general, they are trained on a data set and they have an architecture that is defined. So this is an example of a temporal convolutional neural network, which is a common way of processing audio. And the issue with this is that TCNs or neural networks in general, they might be trained on a data set that's a specific sample rate, and they might require a certain number of samples. So your neural network might have very different requirements than your DAW. So you need to translate between the two seamlessly. And this is like not trivial at all. And the rabbit hole that everybody goes down when they start to write a universal VST for neural audio effects. So the SDK kind of handles all of this for you and is trying to make your life as simple as possible, that all you need to focus on is building a model, but you don't need to focus about all these kind of details that will bog you down. So we kind of had these two worlds that are apart from each other and need to be bridged. So we have the DAW world where you have sampling rate, a buffer size, stereo or mono tracks, and delay reporting. And this can change at any time for any reason, and every computer might be different and have different capabilities. And then we have a Neutone model, so something like a a neural network, or what Andrew was showing, these timbre transfer models, which have a fixed sampling rate because they're trained on a specific data set with a fixed sampling rate. They also require a fixed amount of samples. So for example, a lot of the timbre transfer models require 2048 samples. And they might have a weird combination of stereo in and stereo out. So the other thing with neural models is that they can have any combination of mono and stereo. You can have a model takes in 2 channels and outputs 1 channel, or what's even cooler is you can have a model that takes in a mono audio track and then encodes it into a latent space and then samples that latent space slightly apart from each other, create a stereo effect. So there's these unique possibilities that neural models enable, but we also need to handle these kind of more like kind of weirder scenarios where you have mismatching channels and things like that. And then finally, the model also can introduce delay, which then needs to be returned to the DAW and also needs to be accounted for if the sampling rate is different. So overall, we need to guarantee that the model requirements are maintained and guaranteed while we handle any combination of DAW settings. And this is kind of the thing that we thought might not be that difficult and ended up being a lot of engineering effort. But I think we've reached a point where it's quite nice because we can do a lot of the things that we're seeking to do here. And the way we do this, for a high-level overview, is for sampling rate, we do automatic model sampling rate selection. So models can support multiple different sampling rates or even all sampling rates. And then we do real-time resampling to the correct rate automatically, so that your model is always receiving the correct type of audio. We do a lot of buffer and like automatic buffering of samples as they come in to ensure the model always has the correct number of samples, and this is also not easy to do. We do automatic mono stereo conversions. This is a bit easier, but this is also handled for you automatically. And we do automatic delay reporting, which becomes non-trivial with the buffering and the sampling rate. And I'll give an example in a second where it becomes very clear why this is hard. So here's a concrete example. Let's say we have our DAW is set at 44100 kilohertz and as a sampling rate, and then we have a buffer size of 128 samples coming in with a stereo track. This is a pretty typical scenario. So then let's say we have a Neutone model that was trained on 48 kilohertz with a buffer size of 512 or 1024. So the Neutone will automatically select the best buffer size and sampling rate. And in this case, it's quite easy because there's only a few options, but it can sometimes be non-trivial. Then we're going to calculate the resample buffer size. So for going to 44100, we have to resize to 139. And this is now the internal buffer size of Neutone. And then we can calculate the minimum buffering delay, which is from waiting for the buffers to arrive. And this number can be very weird to calculate because it depends on kind of the remainders of the 2 buffer sizes. And if they're kind of a very weird ratio, for example, 139 is kind of a non-even number, this calculation can become strange. And we support any buffer size. So you can, it doesn't have to be a power of 2, it can be anything. So we have to be able to support all these weird numbers, and we can't really make any assumptions, because even if we only say, powers of 2, once you have to resample to another sampling rate, that number can change drastically. So Neutone handles all of this, calculates the correct numbers, and then allocates all the internal buffers and queues to prevent any memory allocation happening when you're doing inference, which is when the audio needs to come out in real time. So then now for a concrete example of what happens to the audio. So you'll receive a buffer from the DAW, and this will be on the C++ side for the VST. And then we move the buffer over to the Neutone SDK. So everything in the gray box with the dashed line is actually happening in Python, which is then compiled to C++ using TorchScript. So this is how we can enable a ton of flexibility with the SDK while still being reasonably performant and running it in an SDK. And all of this is also happening in a background thread. So this helps us be a little bit safer, because running a neural network is inherently not necessarily a real-time operation. So we move the buffers over background thread. And then in this case, we have a Neutone model that takes as input mono and output stereo, which is similar to the example I mentioned earlier. So we will convert the buffer to mono automatically, and then we're going to resample the buffer to the correct sampling rate, which makes it slightly bigger. And then that buffer is going to be put into an input queue of mono audio, which will guarantee that the model will always have enough audio to work with, no matter what the buffer size is of the DAW. And then the model will take buffers of 512 samples, which is what it was designed for, and then process the audio, output it into an output queue, which is now stereo because the model outputs stereo. And then that gets resampled again to the correct buffer size, which is then output to the VST, which then gets sent to the DAW, and that's what you hear at the other end. So all of this is kind of happening thousands of times to generate the audio. So the reason I think using Neutone is really nice is because you don't need to worry about any of this. All of this is taken care of, and it gives you much more freedom to use whatever neural networks you want to use without having to consider these very strict limitations that DAWs kind of impose. And we try to make your life easier by also providing a bunch of features in the SDK. For example, we include cached convolutions, which are very important for real-time audio effects that are streaming. So they're operating on audio as it comes in. So this is included. We provide temporal convolutional networks, which are a very common audio effect and run very fast. We have highly efficient circular audio queues that let you, take care of queuing audio and samples without you having to worry about it. And this also gets all compiled to C++. And for example, we can handle a look-behind buffer. If you need a lot of samples at input, but output a smaller amount of samples, you can do that easily with a look-behind buffer. And finally, we also give you a profiler, which lets you check how fast your model is running and can give you an idea of if it's real-time or not. And yeah, so the SDK enables rapid prototyping because it's compatible with most DAWs, like the Neutone, the plugin runs in most DAWs, and it lets you load and export models locally. So you can just run your changes really quickly and then load them into the model, and that's good to go. And one thing that's cool is you can use Ableton or something else to map the parameters of Neutone to a physical MIDI controller. So that means you can explore, latent spaces of models, or, something that might be very awkward to change with the mouse with your hands kind of in real time. So you can get a lot of these happy accidents that, only can occur when there's a very creative session where you're not hindered by the interface that you're using. So that's another benefit. And then finally, recently, we also added a spectral wrapper, because right now the SDK was built for audio to audio effects. So this means you're operating on the raw waveform, which is kind of the default, I would say, for many audio effects. But there's also audio that deal with spectrograms, like a spectral delay or a spectral filter, or Ableton recently added 2 spectral effects as well. So like spectral reverb is one of them. So we wanted to add the ability to work with spectrograms because some people prefer working with kind of images rather than raw waveforms, and it opens up a new type of audio effect that you can that you can work with. So neural networks that are optimized for spectrograms exist and can be used to create more interesting effects. So the spectral wrapper in the SDK, it takes the incoming waveform and converts it to a spectrogram, which then can be used by your model to manipulate. And then you can give it a modified spectrogram, which then gets converted back to audio automatically. And a really big issue with spectrograms is phase information, because it's hard to recreate the phase on the other end. So we provide the option where you send the phase information over so that you can deal with the magnitude spectrogram, but keep the phase. And this is useful for, effects that are just changing how much of a frequency are in the signal, but not like wants to preserve the phase. So some things you get for free with the spectrogram wrapper is you can have different spectrogram modes. You can work with a strictly positive spectrogram, so you can ensure it's between 0 and some positive number. You can make it logarithmic. A logarithmic magnitude spectrogram is really popular. You make it a power spectrogram. You can save the phase information. There's different modes for that. And most importantly, it supports crossfading correctly, which allows you to make very smooth effects, because the edges of the spectrograms can be kind of slightly different, which can create an artifact when you put them back together. So this ensures that you have kind of a nice, clean audio coming out once you've converted back. And we've implemented this that, once again, it minimizes dynamic memory allocation so that it runs as fast as possible on like in the C++ world. And there's other common errors that can trip you up with work, like when working with spectrograms. So that's why we encourage using it as well. So I'm just going to give a quick tour of the SDK, and then we'll move on. So when you use the SDK on GitHub, you'll see we have a couple different folders. So the main thing you want to look at are probably the examples folder, and actually the README is probably one of the best files. So the README is probably the first thing you want to look at. It includes a lot of information about what's going on and how to use it. And for those of you who work with Python, it should be quite familiar. And for those of you who aren't, it should still be a good starting point, because like I said, you can also use these Colab notebooks that do a lot for you and do it step by step. But once you're familiar with that, you can check out the clipper, which is kind of our very first starting model. A clipper is a very simple effect. It just clips the audio and distorts it. And it's not even a neural effect, but it's a useful place to start because it's probably the simplest thing you can implement. So for the clipper, you would have a model which does the clipping action here. And then the important part is the SDK. It takes about 10 minutes to wrap a model. So you would basically import Neutone in Python and then create this waveform to waveform base, which is the wrapper that we wrote to wrap your model. And then basically you just have to implement these different methods. So the name of the model is a clipper, the authors, the description, maybe some technical links, and the version number if it's experimental. And then here you can define up to 4 parameters that do different things, like minimum, maximum, and gain, which is typical for a clipper. And here you would want to say whether the input is mono or stereo. So this would be false because it's stereo. And then here you would also give the sample rate. So a clipper works on all sample rates, so you can just leave it empty. And it works on all buffer sizes. It can also be empty. But for example, for other models, you might want to guarantee 44, 100, and here you might want 512 samples or something like that. And then in the forward pass, you would simply define that you get your parameters out of, they're passed in here in the dictionary. And then you just do the forward function of the model and return X. So this is a very simple example. And then the other example I'd like to give is the spectral filter. So this is what I was just talking about, where we have a spectrogram that we want to work with. So for this model, it's just implementing a pretty simple filter where it gets a spectrogram and then attenuates certain bins in the spectrogram using a kind of filter shape. The details of this aren't so important. You can check out the comments if you want to see what's being done here and just play with it. But once again, for the spectral filter wrapper, you would define your model, and then you would say how many frames of the spectrogram your model So in this case, we have 16 frames, and then some spectrogram parameters like 2048, bins, and a hop length of 512. And this is the crossfade, which is very important because it ensures that the output audio doesn't have any artifacts. And then it's very simple. We initialize this real-time SDFT class here, and then we simply fill out the same methods as before. And then in the forward function, which is the one part you have to fill out, you get your parameters. So in this case, it's a notch filter. So we have a center frequency, width, and amount. We convert to a spectrogram. So here we do sdft.audio to spec. And then here we can pass the spectrum into your model, which then converts the spectrogram. And then here we convert it back to audio. And that's it. So it's 4 lines of code. And this model is up here. It's taking the spectrogram, it checks where the bin is, and then it makes it smaller by multiplying it by some factor. So this is how the filter is working. And then lastly, I just want to, if you're interested in all the other options, you can go into the Neutone SDK, which has this waveform to waveform file. And in this file, you can see all the different methods that you have access to. For example, you can get look behind samples. So here you can override this method to provide 512 samples of look behind. So this is very useful if you're dealing with that. Or, if you're just interested in what's happening under the hood, you can see what's going on here. And lastly, we have a profiler. This is profiling the Clipper model. So just an example. You can just run this and it will profile the model and then output, how fast it is and what's going on. And you could replace this with your model quite easily up here. So this can give you an idea of whether your model will run in real time or not. But the easiest way is also to just try it in your DAW and see how it sounds. Usually our ears are a very good indicator if things are going well. But yeah, I think that's everything. I'm gonna pass it on to Naotake, who's going to give some examples of training your own model. And I hope, just to wrap up, the SDK basically is trying to make your life as simple as possible. And it gives you the ability to write code in Python that then becomes a VST, which is very, very nice if you don't want to write C++ code, or if you want to do these kind of complicated neural models that might be very difficult in a C++ world, while also handling all the DAW requirements and all the things that are non-trivial in the background. So yeah, I'm gonna pass it on to Naotake, and you can take it away.
Right, let me just share my screen now. All right. Okay, so I'll be discussing how to create models using Colab notebooks and etc. And I'll also be giving a brief overview of neural audio effects in general. It's there's no math involved today, so don't worry about it. So basically real-time neural audio effects is a pretty upcoming field, and I guess it can be split into 2 main directions. The first is effect simulation. So basically you train a neural network to replace a conventional effect module. So this network is trained to predict the wet signal from the dry signal, and in that sense we call that a supervised sort of problem. Yeah, so it's basically the same as black box modeling, which is also an existing technique, I guess. But yeah, but modeling the effect using a neural network sometimes allows us to modify it, sort of bend it in different ways to get cool sounds, and that's also a big advantage of this approach, I guess. An example is time convolutional network. Yeah, so time convolutional network, I'm going to give a brief overview of the Colab notebook, and you can train that. I mean, we're going to show how to train that in this stream right now, after explaining a bit. And the second type of model is timbre transfer model, and I guess you've seen like the examples by Andrew. So timbre transfer converts the input audio into that of like another instrument or just, I don't know, generic sound like timbre. And this is like type of an unsupervised problem. So to get like a violin sort of timbre transfer model, you just get a bunch of violin sounds and train the autoencoder. And so, and that model would like allow you to like transfer any sound into violin, because the way the autoencoder works is that this autoencoder is trained to like reconstruct the violin sounds. Like the input is the violin and the output is the violin, and it compresses the information and all that. So this intermediate Z variable is like called the latent variable, and that sort of encodes the musical information like performance, like pitch, loudness, etc. And when you feed the network like piano sounds or like any sort of like out of domain sounds, the encoder sort of extracts the musical information and reconstructs that, but the decoder only knows how to like create violin sounds, and that's how we get like a timbre transfer effect. There's like two main timbre transfer effects that we currently support for Neutone. The first is rave. So the rave network is it directly models the raw waveform of the audio. Wait, well, okay, so like the first, I got the first sentence is like the explanation for the DDSP model, sorry. So Rave doesn't like make any assumptions about its like the audio it's modeling, it just models the raw waveform. So you can model like, you can model harmonic sounds, and you can also model percussive sounds. It can be all noisy and stuff. And you can model anything, and that's like the advantage of rave models. The disadvantage is that like it's more expensive to train compared to the DDSP model. It's like 3 days on an average GPU, and you also need like more training data. At least more than 2 hours is good. The author recommends like 3 hours or something. And it totally depends on like the data, like type and like characteristics, I guess. But it's difficult to say like whether your data is good enough or not. And that's like the difficulty of experimentation, I guess. And the second model is the DDSP. So DDSP model predicts the timbre from pitch and loudness that's extracted from the input audio. And the advantage of that is like it follows the original pitch very well, because it explicitly models the fundamental frequency, which is pitch, and the loudness. And also it's this like sort of architecture utilizes what we call like a inductive bias in machine learning. But so it utilizes like the characteristics of a musical signal, which is like usually composed of like harmonics and plot noise. And this knowledge is like encoded into the model. So it's pretty efficient. But the big disadvantage is that it's only for monophonic pitched sounds. So like you can't have like a drum loop, or you can't have like two violins playing like separately. So like, I guess like for like sort of out of this world type of sounds, you want to use rave, but for like traditional instruments and stuff, DDSP is pretty suited for that. So we have like 3 Colab notebooks that like you can train the model, and then you can wrap the model with Neutone and like export it. So the first one is the TCN, which is like effect emulation, a simple effect emulation model, and the rave timbre transfer and the DDSP timbre transfer. And today I'm going to be going over the TCN. Okay, so this is the Colab notebook. Let me just keep. So first we install like the requirements and import stuff. It should be pretty fast. but I mean, like we have to connect to a runtime right now. So let me just, yeah, so let me just explain what goes inside like a TCN model. So this TCN model is like a 1D convolution that operates over like the time. So so this TCN network is composed of TCN blocks, which are this convolution, 1D convolution. You know, convolution, I think you've heard of like, I mean, if you're not familiar with machine learning, you've still heard of like IR reverbs and all that stuff. It's the same operation, but like these, yep. Okay, seems like it's installed. Yeah, and like we define a TCN model. It's yeah, there's like causal convolution and all that stuff, which I will explain a bit later. And so we first upload like a clean sound, a dry signal. Yeah. Okay. So like this is like a super simple example. So wait, we only need like one sound, like pairs. So this is a dry signal. I'll upload that. Yeah, it takes a bit to like upload. Yes, but then I'll upload the wet signal. I'll just use like a low pass version of that. Okay, so like this is a dry signal. Wait, did I share the audio? No. Okay. Okay. Yeah, this is just a dry drum loop. And no pass. Yeah, there's some weird error messages. Like, I don't know. I think like Google doesn't like that I'm using Firefox or something. But yeah, so this is our target signal. We're just trying to emulate like a low pass filter. And yeah, so we'll just do the training from now. Yeah, and it's a pretty simple, it's a pretty small network with like only 4,000 parameters. And it's pretty shallow, and we're only giving it like this pair of data, so it's pretty fast. It says it'll finish in like a minute. That's good. I mean, yeah, like I actually like saved the results, so like we can already hear the results. So yeah, let's just hear the results, okay? So this is the dry signal. And this is the target signal, the low pass. And this is what the network outputted. Wait, this is like, is this the right one? Yeah, I think it's the right one, but yeah, it's okay. So I think I did this one with the reverb. So yeah, let's just wait for the network to finish. Oh yeah, so this is like the loss function values. When the loss function is like decreasing, then it means that it's like trained properly. Yeah, and this is like the actual results. Okay. This network can be used to model stuff like like filters and reverb and compressors and all that. I've tried it with like more extreme like effects like bit crushers and like extreme distortion stuff, but it seems to be a bit worse in terms of that sort of stuff. Okay, so this is a target sound low pass. And this is the modeled low pass filter, like the network output. So you can see like that the high end is like not present anymore, and it's pretty much. I think it's pretty similar, but like not perfect, sort of. So one thing we have to do before we like convert this into a Newton model is that the convolutions inside this model needs to be compatible for streaming, meaning that it has to like take into account that it processes buffer by buffer. If we don't do that, then we get like a sort of a pulse train, sort of well, blips at the start of like each buffer. And then we can wrap the model now. Okay, so we wrapped the model, I think. And now we'll just save this to the Google Drive. The neat thing about Google Colab is that it just mounts your Google Drive like automatically and stuff. So yeah, it's running the export stuff. And yeah, like our time is pretty precious. So like we just say that this it's working fine. Yeah. I already like downloaded the thing. So okay, so I'll just show you how to like load this local model. So like you open the model browser and you press this load your own button. And where did I put the TC and LPF button? Yeah, this is the model that we created. Oh wait, so it's already loaded. Okay. Right. So I'll just play the dry signal right now. So this is another drum loop that's not that's not the training data, but like a different drum loop. And then I'll turn this effect on. So yeah, this is a low pass effect with the TCN that we trained. And then like, you notice that we have all these 4 knobs. So the neat thing about this TCN model is that it sort of automatically finds like interesting parameters to tweak. So like this first knob is controls like how much these 3 knobs do effect on the sound. And so second knob, yeah, the second knob is pretty subtle, I guess. Yeah, the third knob is pretty pronounced. Like it seems to be more of a high pass sort of effect. Yeah, it's definitely cutting the low frequency. So what these 3 knobs are doing is that it's modulating the internal like representations inside the network. Well, it's just messing up like what goes inside the neural network, and that creates like a pretty interesting audio effect. Yeah, so that's about it for this collab. Yeah, so like one thing I need to show about the collab notebook is that there's a sidebar here, and like you can open this and like you can see the files. The Google Drive stuff is like under Drive My Drive or something. So yeah. Okay, so that's about it for the collab notebook. So like the rave time transfer stuff is like pretty similar, except that it takes a lot longer. Rave is a bit like difficult to train like on collab because it's so expensive and like Google wants to kick you out like in the middle of it. So yeah, but people seem to manage, like they're pretty persistent, I guess. Right. So we talked about like this existing models, but you are totally encouraged to like create like new models for Neutone, like alternative architectures. But like in order to do that, so the model has to be written in PyTorch and it has to process buffer by buffer. And yeah, Chris said all this like in much more detail, so I don't have to explain that. But and another thing you have to consider for real-time effects is that if the model is fast enough and if the model is like streamable. So one thing about Neutone is that it operates on CPU. We know that GPU is like great for like neural networks, but it's not so obviously. Yeah, I mean, there's like people like GPU Audio that's like the sponsor of this math competition as well. So like yeah, they're doing great work on like bringing that to like the audio effects, but like most like music production nowadays is mostly on the CPU, and Neutone is also on the CPU. And so models like Rave is pretty complex, but it still managed to be pretty fast on the CPU because it utilizes many techniques like PQMFs and all that. There are like slow models though, like diffusion models that's like making all the rage is pretty slow. I don't think that could like ever be on like a real-time audio effects, like unless a breakthrough. And there are that big transformer models like Audio LM, like it's pretty interesting, but not very like I don't think it even runs on like normal GPUs. I don't know, it's very big GPUs, I guess. And so and the second like requirement is that it is streamable. So this causal convolution is like one thing that really affects the latency of your model. Causal means that it doesn't like depend on future input. So I guess like filters are like sometimes causal and non-causal. Like if it's non-causal, then it relies on like future input to calculate the current output. So it's like that. So like it's like this left diagram. You want to get like the output at step like time t, but you need the input at time t+1, and that totally affects the latency of your model. So you want the model to be like pretty much causal all the way. And another thing is that streaming completion or cache completion. So yeah, I'll just show like a big diagram. So these are buffers, and like this is the first buffer and like the second buffer. So if we apply like non-streaming like standard completion on these buffers, so usually CNNs have like this sort of completions have this sort of zero padding operation. This zero padding is applied to this buffer and also the second buffer as well. So like, but like if these two buffers weren't separated, then there wouldn't be padding between these two buffers. And that creates a sort of discontinuity. Discontinuity, is that spelled right? I don't know, but yeah. So that's like totally like unacceptable for an audio effect. So the streaming completion like takes care of this by like replacing this padding with the end of this first buffer. So yeah, so calculation wise, it'll be the same as if these buffers weren't split at all. Yeah, so it's a pretty like lesser known like technique, but there is some like technique some like libraries for this. I mean, obviously Neutone SDK has the TCN, and you should like look at that and use that for your audio effect, I guess. So yeah, that's about it for me. I would love to know if you have like ideas for models. Like you can, for example, like train these models with like really interesting sounds that you have. So like there's the Colab notebooks, and you could use your own GPU or something, or you could use a cloud provider or something. And yeah, and like you could like expand these models to be like better, like, you know, better controls, like TCNs with like but you actually modeled like knobs of each effects, like the distortion, like gain and all that stuff. And yeah, we'd love to you to see like building new architectures for Neutone. That would be cool. Like this new spectral wrapper is like a good opportunity for that as well. Yeah, so I'll hand it over to Andrew again.
Yeah, cheers, Naotake. That was awesome. Just for the final part of this workshop, quickly just checking the time there. We will show some of the community collaborations and contributions that we've seen so far. So I'm just going to share my screen. Okay, and then I think that's sharing fine. So here we go. Okay, so yeah, we have a number of examples here just quickly to show. I won't go through all of them, in fact, just because of the time, but to kind of give you some of the community that have been like interacting with Neutone and using it as part of their creative processes. We have Big Yuki again. Here he is jamming out on the piano. Let's see if this loads. So in this example, he's using piano through Neutone into like a speech model. You hear that being translated. This is an amen break drum model. Just mayhem going on there, but that sounds so awesome. So, and then this is Naotake from Qosmo jamming out, creating some sort of percussive beats with a speech model as well. I think this is always a fun example. So yeah, just grooving out there. If you want like any of these links to check out the full videos, just let us know. We can post them in the chat. Anyway, I hope that gives you an idea. We've also had some people from the research community use Neutone as part of their research. So we had Caleb Koch from Belmont University use Neutone as part of his experiments, trying to model amplifiers and like amplifier distortion and guitar effects. So he sort of built these models and then like tried them, ran them in Neutone to hear how they sounded. And I think, yeah, made some great progress with amp modeling through that. And this was his poster that he showed off at the end of his project with his results. So it was great to see that. Yeah, so the last, just to conclude on our workshop today, we're really wanting to see more people get involved. We want to see more models be contributed and submitted to Neutone. There's a lot of great architectures and research coming out constantly. It's such a fast evolving space. So, you know, we want to ask also, like, what sort of models would you like to see? And, you know, as models that we want to explore ourselves, you know, there's real-time diffusion being done on like a sort of GPU type inference, which has came out and has been quite interesting. So like a sort of text to audio effect. You know, we've also got like other VAE models like Musica, which generates music in real time. So rather than like translating like a sound to another sound, it's actually generating music, say electronic music or something in real time. We have new versions of Rave coming that have came out recently. We're also interested, and we've heard some people mention that they're interested in running Neutone on embedded hardware, like on the Bella, for example. So we'd love to explore that sort of avenue as well. A bit like Caleb's research, the analog modeling, being able to host and perform tube amplifier emulations like through Neutone as well. Something we want to add more of these models to the Neutone catalog. And then again, veering away from the audio, we're also interested in doing symbolic music generation, so like MIDI generation models as well. And then transformer models, like we may not be able to run those at the moment on CPU, but we'd love to start implementing new mechanisms to actually accelerate some of the heavier weight models on GPU as well. So yeah, so that's kind of where you guys come in, and we hope as many of you as possible like contribute to the Neutone community. We'd love to collaborate with many of you. Like if people have got ideas of great features that they want to bring to Neutone, we'd love to work with you, and please reach out. Let us know what features you'd like to see. We're constantly working on the platform and on the VST functionality. We'd like to bring MIDI to audio models in as well, and like that I mentioned earlier, offline rendering for heavier weight neural audio models. And yeah, UI UX, I think that's super important to think about when it comes to these new technologies. Like what interesting and exciting ways can we interact with neural audio models, especially for like live performance and composition. So ideas on how to do some new interactions with these models is also welcome. Your suggestions are welcome there. So and yeah, and extending our SDK as well, adding, it's open source, you could fork it, you can add features to it and really make it your own. And these are all the people that have been involved in this sort of a Neutone to date, like getting to where it is. Our team at Qosmo, and obviously the guys at Arcam for allowing us to use the Rave algorithms as models and host these models part of Neutone. So yeah, that's our credits. And yeah, thank you everyone for listening and following along. We'll share all our resources with you in the YouTube and in our Discord as well. So make sure to check out our Discord, because there'll be lots of resources there. We also have the Neuro Audio plugin competition channel in the Audio Programmer Discord. So be sure to go there too for more resources and information. And these are just some of our links as well, just to keep them at the forefront of your mind and to check them out. But yeah, thank you very much for watching. I think we're good to maybe take some questions, and then we can move on to the next presentation.
Yes, thank you very much, Andrew. And what we'll do is we will wait for a few more questions. There is a question here from Christopher, who asks, I know this is a shot in the dark, but will there ever be a TensorFlow SDK for Neutone?
So TensorFlow, we've been so at the moment we're only using the PyTorch framework for TensorFlow, as it kind of is compatible with how we've designed the plugin. Also, PyTorch, the way the framework's built, makes it quite nice for this sort of wrapping and exporting mechanism for the Neutone plugin. But we have been interested in exploring other options that allow us to bring in users of other frameworks to Neutone. So one solution to that is maybe using a framework like Onyx, which allows you to exchange and swap between different major frameworks. So Ollie Larkin, who was on last week, was showing an example of using the Onyx runtime. So the great advantage of Onyx is that you can go from a PyTorch model to Onyx, or TensorFlow model to Onyx, and then use their Onyx runtime to actually perform the model that you've converted. So there is that potential avenue, but I think for the time being we'll be concentrating on the PyTorch version, but we are thinking about ways in which we can extend, yeah, to other frameworks as well. But yeah.
Great. Yeah.
Oh, sorry. I just wanted to say, I saw in the chat a question about sustainability that I think I'd like to talk about a little bit. So in machine learning, there's this big problem of we want to build models that run on electricity that use up a lot of energy. And I think the question was asking, first off, how do we balance training these models versus, causing more CO2 emissions? I think there's kind of three ways to answer this. So the first is there's like a really big push in machine learning, which is typically done by tech companies that happen to be more focused about the environment, I think, than some other companies to be more green. So I know Google Colab is trying to be like fully green with their data centers by 2030. But regardless, of course, there is that. And then the question was, aren't you wasting energy by training, trivial effects on a GPU? But I think the effects that we're showing here are more simple examples on how to get started. And you saw how fast they train with Naotake's code. So it's equivalent to kind of running your microwave for a minute. So I think in the grand scheme of things, compared to like large language models, these audio effects are orders of magnitude faster to train in some cases. But then I guess the last point I think that's good to notice is another way to think about it, even though we want to reduce energy use as much as possible, is as more people get into audio production, which is becoming more and more popular with like the computer, there's also this demand for audio effects, right? And I think some people might go out and buy hardware, which is very, really nice to use, but also has its own huge problems with electronic waste and the use of energy to create hardware. So there's another argument to be made by giving people more effects that are virtual. You could be saving energy on that side or preventing some of this e-waste that could happen from guitar pedals being bought as more people get access to the technology. But I think there's just multiple ways of looking at it, and there's not really the right answer at this point in time. But I think there's hope for the future as well for this.
Fantastic. Stake Proof says, I appreciate you taking the time to answer a difficult question. So thank you, Chris. And thank you to Andrew and Naotake for staying up. I know it's quite late for Naotake in Japan. It's probably about 3 o'clock in the morning over there, or possibly later. So thank you very much for your contribution. And with that, looks like we're done with questions. Thank you very much, Team Qosmo. There is one more question here from Gary Worsham. How big of a pitch range is required for the training signal?
I guess it might be about the DSP model, I guess. It depends, I guess. So like if the model is trained on like a certain pitch range, then it's going to respond to that certain pitch range. So
right.
So if your model is like a bass model, I guess you don't really need a really high-pitched bass sounds, I guess. Like it's just a natural, like, I guess, pitch range, I guess. But yeah, that's my answer, I guess.
Yeah, sounds good. Great. Looks like that's it for questions. Thank you again, Team Qosmo. And with that, I will go ahead and move along to our next talk.